Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to summarize this entire section since it was extremely long. It's amazing to think that we did all that just to play tic-tac-toe, and we haven't even yet seen the main reinforcement learning algorithms in this course yet. First, I asked you to think about how you would solve tic-tac-toe as a naive first-year computer science student. The answer was that we would end up building an agent with a bunch of if statements. It wouldn't adapt to its environment or get better as it played more games. So even if it seemed intelligent at first, it would never be able to increase its intelligence. Moreover, the algorithm would not be generalizable to new games. It would only work for tic-tac-toe. So we've set out on this course to find algorithms that are intelligent and that allow an AI to solve anything given the right rewards. Next, we took a deeper look at the components of a reinforcement learning system. We defined the agent, environment, states, actions, and rewards. We talked about how specific reward structures can lead to poor results, so we need to choose them carefully. This is like you choosing how to reward your dog in order to train it to behave well. We looked at new terms like episode and terminal state, which we needed to fully understand the algorithm we used for tic-tac-toe. Next, we looked at the credit assignment problem, and closely related to that, the idea of delayed reward. The idea was that an action you take now may not lead to a good immediate reward, but it may maximize your future rewards. So you want to be able to plan intelligently. We use these to motivate the idea behind the value function. We saw that based on how the value function is updated, if we initialize it in the correct way, such that the value of a terminal state is 1 if we win and 0 otherwise, then the values will propagate backward along the state history. We do this iterative update in small steps at the end of each episode, so only the possible next states can influence the previous state. Finally, we put all this together in code, and you saw that the algorithm does indeed work, and that the tic-tac-toe agent, once it's trained to play tic-tac-toe, makes intelligent moves. Now that you've had some experience with reinforcement learning, it's interesting to look back and try to compare it with supervised learning. One common question is, why can't we just create a supervised learning problem that maps states to actions directly? The first problem with this is how we would come up with labels. As you've already seen, it's extremely easy for the state space to grow too large to enumerate. Tic-tac-toe or Connect 4 is probably the limit. Imagine a video game with HD graphics and 60 frames per second. Now you have millions of pixels with hundreds of values per pixel and 60 of those per second. The number of possible states in a game like this is so large you probably can't even conceptualize it. So there's no way you can create proper labels. There's also the fact that labels only tell us if we're right or wrong. In a way, a reward is more flexible and gives us information because it tells us how right or how wrong. Rewards tell us how good we're doing. Rewards are delayed, but the value function has this information built in. If you're trying to choose the best action for a particular state, so assuming somehow you get around the problem that you need to label an exponentially large dataset, you still need to choose the best action based on all possible future rewards. So that means you would need to be the one calculating the value of each state and choosing the best action based on those values. In other words, instead of letting an algorithm calculate values in a way that automatically accounts for delayed rewards, you would need to somehow keep track of those yourself. Rewards can also have a component of randomness. So sometimes when you go to a state, you get a reward of 1, but other times you get a 0. This could be like you study for your exam tomorrow, but then tomorrow there's a snowstorm and your exam is canceled. Next states can likewise also be random. In reinforcement learning, we are never told externally if an action-state pair is good or not. The only way we can find out is by discovering it ourselves by performing the action. Finally, reinforcement learning is completely online. We learn as we play. Every time the tic-tac-toe agent plays an episode of tic-tac-toe, it gets better. Compare this to a decision tree. It takes all its training data in at once and creates a tree based on that. If you want to incorporate new data into the tree, you need to start all over again. So I hope this gives you some further insight into why it might seem like supervised learning can be used for reinforcement learning tasks, when in fact this would be an infeasible task.